My
Yeah.
fingers were okay. So it was just I forgot to plug in something. That's really all that happened. So the question we're going to do is 8 instead of 7 through popular demand. Evidently, and I can understand why this one's going to look uglier. You're being asked to find the unit tangent, the unit normal, and the curvature function. Now, technically, these things have a t attached to them, but sometimes they just write Tn and kappa, and we all understand that it's not a single vector with just numbers in it. It's a vector function, right? There's t's in it, typically. So order is interesting. Which one shall I do first? I'll do it in the order they ask. Now, let's find the unit tangent. Now, the formula for the unit tangent is that you find the first derivative of your space curve and you make it a unit vector by doing this to it. So that's where I'm going to go first. So this is, God, that's a weird number. So I'm going to first get its derivative. The fact that that's a weird number doesn't actually make its derivative that difficult. It's that. Do you know that e to the 3t, when you differentiate it, you do a little chain rule thing, and you do a little chain rule thing here? Are we okay with that step? Pretty standard derivative of each 3 pieces. That's our dash. Now, the ugly, probably one of many ugly things that's going to happen in this question. We then find the magnitude of the vector, because that's what's going to go here. And to do that, we basically take each of these terms and you square them and you add them all together. And I'm going to work on the principle that that better be a perfect square. Otherwise, we're going to go south really quickly. Three root 2 times another 3 root 2. God, what does that get you? It gets you 9 times
18.
Thank you. This guy gets you 9e to the 3t, and this guy gets you 9e to the negative 3t, and yes, it is a perfect square. Now, it is not written in the order big to small, because if you want to convert a perfect square into its perfect square, you need to have that kind of structure to figure out what the bits are. So all I'm doing...
e to the 6t and e minus 6t? Yeah.
Thank you. Now, I'm not keen on proving that this darn thing is a perfect square, that I almost screwed up on the incidentals. Actually, if I'd left that guy as 3t, I would have quickly figured out that it was wrong, because the perfect square thing would have fell apart on me. Right, now, when you are a perfect square, well, let's start going back a little bit. You know that if you want to simplify these things, there's really going to be, it better be a number, right? It better be the square root of 42, something like that. That's easy to deal with, right? If you're going to get further up, if there's 3 terms, doesn't it typically mean that it's a perfect square? That's kind of my clue. 3 terms inside the square root are probably going to be a perfect square. Now, this guy gets me 3e to the 3t. This guy gets me 3e to the negative 3t, all squared. That is him. That might not look like the square of him, but nonetheless it is. Isn't the rule you take the highest power and square root everything? So 9 gets you 3, and 6t gets you 3t. Right? And on this side, 9 gets you 3, and half the power of e to the negative 6t gets you e to the negative 3t. but I think I should prove it. If I'm correct, which God, I'm finger crossing here I am. Yes, I am. Where's my confidence? Then when I FOIL this, shouldn't I get this? Well, let's see what we get. That times that gets you 9e to the 6t. Check. What does these two guys get you? So if you multiply e to the 3t with 3 times e to the negative 3t.
Gets you 9 times 1, yeah.
And that's 9. Now, if you do the other one, can you trust me, you get another 9? And then you do the last guys and you get 9e to negative 6t. It's almost like magic, isn't it? That the structure just kind of collapses into, I wouldn't exactly call this simple, but at least you can live with it, right? There we go. Now, you put those together, and the unit tangent then is 1 over this fella times the derivative guy. And the derivative guy is not that pretty. And that's an understatement. So I'm going to do minor cosmetics. I'm going to pull out a 3 out of that. I'm going to pull a 3 out of this. And then I'm going to cancel those 3. So what do I end up with? I end up with root 2 over that guy, e to the 3t over that guy, and negative e to negative 3t over that guy. Or you could pull it out if you like and have it as a multiple of this guy, which is probably a little bit nicer. So I guess I'll show you what that looks like. How did that go? Did when you were looking at it, did the perfect square just not come to you, or did one of the numbers, like I got a 3 when I should have had a 6? Okay. Now
I just had troubles with the square.
Yeah. Well, it doesn't even look. I mean, when you look at it like that, it does not look like a perfect square. In fact, if you keep it in that order, it's not going to generate the perfect square, because if you keep in that order, aren't you going to call that a square root of 18? And then you're going to call that, well, that's pretty good, right? You're going to call that 3e to negative 3t. But you stick them together and it doesn't make this, right? So when you look at a square root with 3 terms inside it, well, you make sure that you put them in order of biggest power to smallest power. So in this case, it's e to the 6t, a constant, and then a negative power, right? That would be the order. And then you might see the perfect square. Now, I'm going to cheat a little bit here. I'm not going to do the unit normal, but I can tell you, looking at that guy, I'm going to be spending another 20 minutes doing it. I can just see. Can you imagine how difficult the derivative is going to be?
Well, like, that's why I wanted you to do this.
Ah, right. But what I am going to do is I will do that guy and I will put that guy up online as a PDF and let you go through it slowly.
Perfect.
Okay? So it's not, I'm not doing it right now, but I don't really want to spend my, well, I don't know if I call it valuable, but whatever, my visual time with you where we can do things that maybe would be more useful. Now, I guess the question is, do you want me to do the curvature on this one? Or do you want me just to add that to the PDF that I'll put online?
If you're gonna post it online, you could probably just do that there. We save more time here.
Okay, are we okay with that? Is it when he pushes into the corner? Right, okay. So, we haven't, what's the word I'm looking for? We haven't finished with the unit tangent yet. In fact, that's going to be my first topic for today. How to find unit tangent, unit normal, and the unit binormal. And once I've done this intro, I'm actually going to go in and pick one of the questions from the homework, because if you don't pick nice starting space curves, these guys, as you've just seen an example, that was horrible. This would be 20 minutes, and that would be the rest of your life. You know, so you could easily just randomly picking what doesn't seem particularly nasty functions could generate atrocious algebra. So I'm going to trust the textbook by picking either one of their own questions or one from their textbook, because then I'm pretty confident that they're going to be perfect squares and they're going to, you know, algebraically become a little bit nicer. So let's show you what you're actually finding when you find these three functions of t. So here is x, here is y, here is z, and here is our roller coaster of death. Now, if you choose a point on the curve, you know, the point would be generically point with t equals t, right? The generic, any point on that curve. If you find the first derivative, you get a vector that looks like that. That's r dashed of t, right? But if you make that 1 unit long, that's what the unit tangent vector is. It's a unit, it's a vector in the same direction as the first derivative. Another term for that is velocity, but 1 unit long. It's a bit like a standardized direction. You know, like I, j, and k are standardized directions, one in the x, one in the y, and one in the z. This is a standardized direction going like that. Now, do you see how at this point there's a kind of curve thing going on? Can you imagine a little curve thing? If you take the second guy, which I haven't told you how to get him yet, but he's called the unit normal, what you get is a vector that is okay, analogy. You're on the roller coaster to your death, right? Isn't the unit tangent the angle you shoot off, right? The vector that you shoot off to your direction, right? That's him. Imagine it wasn't broke. If you're on a roller coaster and you go round a bend, isn't there a sideways motion that you will feel in the direction of the curvature that you're curving round the bend? You've been in a roller coaster, when they go round the bend, you kind of feel this tug. Can you think of that as being the force or the direction of the normal force? Now, there's a third one called the unit binormal. And the unit binormal, in this case, it doesn't need to be vector, it just happens to look vector here. If you're in your roller coaster and you do certain curvatures, do you sometimes feel that force that's lifting you out of your seat? Or sometimes pushing you into your seat, right? Depends on which way the curve's, you know, doing its thing. That's a bit like what the binormal force is. Now, here's something that my picture may not show you. Do you know that those three forces, those three vectors, the unit tangent, the unit normal, and the unit binormal, they are all perpendicular to each other. So what they sometimes do is that if you have a space curve and you want to simplify the components, right? The way it's written. It's sometimes much better to change your axes. Instead of your arbitrary X, Y, and Z axis, you change them into some standardized unit tangent, unit normal, unit binormal axes. And when you do that, the algebra can very often become much simpler. And also you can get some insight into what that object's movement is really looking like in 3D space. So there's a sort of a motivation behind that. Now, I haven't told you how to get them yet, so let's show you. If you want to do the unit tangent, we know how to do that one. We just did it a few minutes ago. It's that fella, that multiple of that fella, right? Now here's the unit normal. Now to get the unit normal, you differentiate the unit tangent vector and then you make it a unit vector. Now I know the unit tangent vector is a unit vector, right? It's 1 unit long, it's designed to be. But you know its derivative doesn't necessarily have to be 1 unit long. It might be a half a unit long, it might be 2. So you make it 1 unit long by dividing by its magnitude. And the last one of the 3, the unit binormal. You just take the cross product of the other 2 and that'll guarantee you the unit binormal. So can you see that these 3 guys, the unit tangent, the unit normal, and the unit binormal, basically involve finding unit tangents to vector functions. Most of the time you're going to be dealing with vector functions with t's and t cubes and e to the t's and whatever. And so the algebra will be quite heavy.
Can you cover what you have to actually do to get the unit normal again? Just like the verbiage.
Right. What you do here is you take this answer, right, the one you've just found. You differentiate them, and then you divide by its magnitude. So if you imagine, let's just pretend I did a unit tangent and I already found the answer and I'm making my life easy, that it was this guy. Right? Then if I wanted to get the unit normal, I would differentiate this guy.
Excuse me, Mr.
Yes.
Robinson.
Yes.
Interpret the binormal vector. Like, why do we need to know it?
The binormal vector gives you the third vector, the third unit vector that allows you to do what's called a vector basis. It allows you to create a different way of orientating your 3-dimensional space so that the space curve that you're interested in can be written down in a simpler format. So instead of saying the thing in terms of X, Y, and Z, which very often generate ugly results, you can give it in terms of these 3 vectors. And that makes things actually a lot simpler. I'll give you an example. Do you know the unit tangent and the unit normal, just those 2, make a little thing like this? Do you know your acceleration vector is in the plane of those 2? All the time. And that things like that.
Sorry, internet connection is bad.
Oh, I apologize. Well, I'm not sure I can apologize, but I feel your pain. Right, back to this guy. You differentiate him. You find his magnitude. And then the unit normal will be 1 over this horrible guy times this guy. And if you wanted to put it together as a single vector, that would be, that fella there would be the unit normal.
Right.
We're actually going to do one, so I guess you'll see the process a little bit better because I just pulled this out of my hat. I didn't, I just said pretend the unit term tangent was this, and it's a bit like deja vu. You know what you do to make this happen? Don't you do the same thing, but using that as your starting point? So you get your unit tangent by doing a certain process. You then use that as your starting point and you do the process again. Do you think if I did the same thing to this process, I would end up with the unit binormal? And the answer is yes. But isn't it easier just to take two cross products of two ugly guys that you've already found than fight your way through yet an uglier, because they tend to get uglier and uglier each time you do this process, an uglier function. We good? We're thumbs up right now. Okay. Let's zoom out and in. Well, actually, I am going to risk. Watch this. This shows how brave I am. I am going to risk my own function to do those three things for. And I'm going to pick a function that I think will come out relatively nice algebraically. Because if they don't, it'll take us half an hour. Has anybody any idea what kind of space curve I'm going to start with to find the unit tangent, normal, and binormal?
A helix?
Yeah. Can you imagine why I chose a helix or why I think a helix is going to be my friend?
Straightforward derivatives?
They are, and they tend to come together nicely, don't they? Especially their magnitudes. Don't their magnitudes tend to become just numbers? Right? Which is a good thing in this process. So, I am going to do 3t plus 1 4 sine t 4 cosine t. There's a helix spiraling along the y-axis, right? Can you imagine it doing its little thing? And since these are the same, won't it be circular if you looked along the x-axis? You'd see a circle spiraling towards you, wouldn't you? Right, so first thing, find the derivative. 3, 4 cosines, negative 4 sines. Find the magnitude of the first derivative. 3 squared, 4 cos squared, negative 4 sine squared. Nine. Okay. Can I jump into plus 16, or do you want to see where plus 16 came from?
Didn't we learn that yesterday?
Yeah. So I'm basically skipping a line here, which I don't typically do, but this is going to be a long question no matter how nice it is. Won't that get you 16 cos squared? Won't that get you 16 sine squared? Don't 16 sine squared plus 16 cos squares just come together and give you 16? We go?
Yes.
Right. So
What happens
that's
with the negative from the sine t? Just
well, your negative times itself gives you a positive, so you still
great.
get positive
Yeah,
16. So this fella here gets you square root of 25, and that is a nice value for the magnitude. You see it's a number, it doesn't even have t's in it. That will make my life easier. So our first one in the set, the unit tangent vector, is 1 over the magnitude of the derivative times the derivative vector. So in this case, 1/5 of here. So that's 3, 4 cosine t, negative 4 sine t. So up here, I will put the unit tangent vector. He is 3/5, 4/5 cosine t, negative 4/5 sine t. Are we good? Because I'll lose track of this guy. I'll put a bubble around him to remind myself that's one of my answers. Now, I want to find the unit normal. The unit normal vector is given by that. So essentially, don't I do what I just did, but use this as my starting point? In other words, differentiate this. That goes there. The derivative that I just found, don't I find its magnitude? That way it'll become a unit normal vector. So let's see what we have here. Well, if I differentiate this fella, I get 0. I get negative 4/5 sine t. And I get negative 4/5 cosine t. I now find its magnitude. Zero squared, negative 4/5 sine squared, negative 4/5 cos squared. And what does that get me? It gets me 0, positive 1625 sine squared, plus 1625 cos squared. Oh, isn't that pretty? What do they two eventually become when you add them together?
16 over 25.
And 16 over 25,
That breaks down beautifully.
helixes are such lovely shapes to do this process to. And it's still a long question, by all means, it's a long question, but at least it's kind of in the realms of I can still handle it, right? I can still see what all the bits are going to look like. So when I put these together, the unit normal then is 1 over this magnitude, which is 4/5, and the derivative vector, this guy. So it's 0, negative 4/5 sine t, negative 4/5 cosine t. I really do want to make that look prettier. Isn't 1 over 4/5 the same thing as 5/4? And isn't 5/4 going to play really well with these two guys? So what do I get for my unit normal? I get 0, I get negative sine t, and I get negative cosine t. So the unit normal is also quite pretty. So far, so good. Unit tangent, unit normal. So I put the package together. And just so I've got them all in one place, you really don't need to write this down, but I am. This is what we found earlier. The unit normal. Now I'm going to get the last one in the set. I'm going to get the unit phi normal. Can you remember how to calculate it? And no, you don't need to go through that same process one more time, although technically it would work. Let's do it the usual way in which they do it. Anybody remember how to calculate it?
Cross product.
Cross product of unit tangent and unit normal.
Yep. So in this case, we're going to do, there's our I, there's our J, and there our K. Is calculating cross products becoming second nature now to you because you've probably done so many?
It's eerie.
Eerie means good, or eerie just means eerie? I'm not sure. What does that mean?
It's kind of like rote now.
Yeah, it's just like 5 times 7. It's my times table, right? It's a lot more complicated than that, but that's what it is. So 3/5, 4/5 cosine t, and negative 4/5 sine t. And then what we have is 0, a negative sine t, and a negative cosine t. Okay, let's see what we get. We get so many i's, take away so many j's, plus so many k's. I hope by now you do it because you're told to, that this negative doesn't disappear on you. You just kind of write it down rote because you know it has to be there, right? So, cover up time. Negative 4/5 cos squared, negative 4/5 sine squared. Can you imagine all those negatives and then one more? So negative 4/5 cos squared, negative 4/5 sine squared, that ends up being negative 4/5. Make sense? Okay, cover up the middle one. If you go this way, you get negative 3/5 cosine, take away nothing. So this is negative 3/5 cosines. I'll cover that guy up. You get negative 3/5 sine t. So we have a negative 4/5. 2 negatives make this positive, and a negative guy at the end. The unit tangent, the unit normal, and the unit binormal. If you know those 3 things about a space curve, and you're into kinematics, right, the motion of objects in 3D space. If you know these 3 things, you pretty much know everything you need to know about that moving object. You can actually, you can do anything you want, essentially, right? Everything is contained within these 3 separate vectors. Are we good? Right. I don't know anybody could tell me this. I know it's true, but I can't remember why it's true. If you are in space and you're way out in deep space and there's no gravitational objects worth worrying about, if you take your space station and you rotate it, can't you generate false gravity?
I've never been to space, so I don't know.
You've never watched a decent sci-fi movie?
Yes, yes,
don't.
yes.
Right?
Isn't that one of the things they do with space stations to try and give it a semblance of reality? Have you noticed that big space stations get rotated?
Mm-hmm.
Now, that's not just for cosmetic. Oh, that's cool, the thing moves. No, there's a physics behind that. And when you rotate an object, a space station, you will generate this vector here. You'll generate others, but you will generate this vector here. If you rotate it the right way, won't this vector be pushing you into your chair? Isn't pushing you into your chair essentially gravity? False gravity, but still gravity. So if you rotate quickly enough, you will generate enough gravity to feel like you're on Earth. You'd have a weird orientation issue, because gravity would be pushing you. So imagine this is your space station and it's rotating. Gravity would be pushing you towards the center. So if you ever watch a decent sci-fi movie, you'll find that people walk along the space station on the outer rim or the inner rim, depending on the rotation that they're using on the gravity. If you go one way, you push it out. If you go the other way, you push people in. It's kind of cool. So you never thought you were going to find out why science fiction space stations rotate, and the reason they rotate is to generate a binormal vector, and a binormal vector will give you the impression of gravity because it will be forcing you into your seat or forcing you into the surface of your floor of your space station, which will make you feel like you're walking on Earth. I'm impressed by myself that I actually got through that without screwing up. At least none of you noticed if I did, and I can't say I did. So, did I screw up anywhere? Yeah, I'm giving myself brownie points today. Okay, let's go now, if we can, and I'm going to pick one more of these. I know that they are time consuming, hopefully not laborious.
These are fun.
There's just to see another one, right? A different one that's not a helix, essentially. And that one I have no chance of making up. Right? Any questions? We cool with that? Okay. Are you looking at the homework question right now? The grid here.
Yes.
Right. So unit tangent, unit normal. No good. That's a helix. Ooh, that's interesting. Oh, we're going to do 8, so there's no point in me doing 8. 7 looks interesting. That's just curvature, that's boring. That's a unit tangent and a unit normal and a unit binormal, but you're doing it at a point. Yeah, that's worth it. I'll do that one. Okay. So this is my version of question 10. The space curve, the reason I'm picking this one is it doesn't have sines and cosines in it. I think question 7, which was my other choice, that one had sines and cosines, and I'm pretty sure that that one ends up being math that is very similar to that in a helix. So you won't really get a taste of, different algebra. That's the only reason I skipped. Okay, I'm now going to leave that and kick back in. And we are going to, oh, got some chat. Any questions there? Okay, where are we going here? Lost the place. And we go. Right. Unit tangent, unit normal, and the binormal at that point. I'm not going to worry about that point really until the end. And in fact, I might not even do that bit. Right. I think I know what's going to happen in the algebra here. This is going to be a perfect square. It's going to be a situation where when we get the magnitude, it is a perfect square. So here goes. 2t, 2t squared, 1. Hey, that was easy, right? Could have been a lot worse. Magnitude of that first derivative is, oops, the square root of 2t all squared, of 2t squared all squared, and of 1 squared. 4t squared. 4t to the 4 plus 1. That is not a perfect square. You bugger. That is not a perfect square. I thought it would be because I'm saying to myself, there are going to be 3 terms. And when there are going to be 3 terms, it should be a perfect square, right? Evidently wrong. I'm going to go out and in for a minute. I'm still going to finish this question. I just want to make sure that I actually wrote the right question down, because that could certainly contribute.
Professor Robertson,
Yes.
wouldn't it just be 2t squared plus 1 squared?
Where are we coming from? 2t squared plus 1. 2t is the first guy, you square it, which is 4t squared. I don't see that changing. The middle term is 2t squared, which is going to generate me 4t to the 4. I don't see that being different. And 1 squared just gets me 1. So I'm not sure what you're telling me. No. I'm looking at the question here, and this guy is exactly the way it is. So I guess I got to fight my way through it. Are we comfortable with that gets you 2t, that gets you 2t squared, and that gets you 1? And then when you square each of these terms, you get that one, and that one. We agreed? Right. Now, you don't need to do this line. In fact, it's not going to help you any, but I'm doing it. Oh, it's a perfect square. Thank God for that.
Yeah, that's what someone was trying to say earlier. That's what they
Oh,
were
I apologize. I thought you were talking about I'd written something down wrongly, not that you'd figured out it was a perfect square. Oh, whew. And I'm the one that told you, write them down in order if you want to do your perfect square. Because the order it was in screwed with my brain. And I didn't see a perfect square because I was wrongly looking at those 2 guys, wasn't I? And I should have been, well, whatever. It's now okay. Everybody's happy. Which means that you get 2t squared plus 1. So our unit tangent vector is going to be 1 over that guy with this fella. I guess I'm going to do this. Now that's as a single vector. Interesting. Now I still need to get the unit normal, and that is going to be messy, but I'll do it. And once I've got the unit normal, I will then evaluate them using this point. Let's figure out what point this is. By that, what value of t for this space curve generates that guy? Well, let's see what we got. If you compare the x components, shouldn't t squared equal 1? Which means that you have a choice, plus or minus 1. So it has to be one or the other, but it can't be both, right? It has to be an individual unique point. So if you look at 2/3 t cubed is equal to negative 2/3, which is comparing the y's, doesn't that make t cubed negative 1? We now know who we're looking at. That guy there occurs when t is equal to negative 1. Okay, right. Now, nope. I'm changing my mind here. I'll do one of them just to show you what I would do, but this is a time-consuming process. Aren't I going to have to differentiate that quotient rule? Differentiate that quotient rule. Differentiate that, well, you can do it as a chain rule. You could technically do it as a quotient rule. 3 really ugly guys, agreed? Magnitude of those really ugly guys. And then we can plug in the numbers. So I'll pick one of them. Let's do this one. Now, if I want to differentiate it, f dash g take away f of g dashed over g squared, what do I get? Well, if I call the top f and I call the bottom g, I get 2t squared plus 1, take away 2t times 4t, all over 2t squared plus 1 squared. And what does that get me? 4 of these, take away 8 of those and 2 of those. I believe you get 2 take away 4t squared over 2t squared plus 1 squared. So 2 take away 4t squared over 2t squared plus 1 squared. Do you want me to do the next 2 and keep going? Or can I just talk through what the rest of this process would be like?
It
No,
might
it
help.
was
Long and
would be
tedious.
awesome.
I heard, right, I'll start with Chris and then the other person. What do you want? What's your comment, Chris?
I was just gonna say it's long and tedious.
Okay. Can we just say a dot, dot, dot and a dot, dot, dot? Right? Now, to get this one, won't you use a quotient rule, not unlike this, but it will obviously be different because of the 2t squared plus 1 in the top. For this one here, there's a couple of approaches. Couldn't you call it 2t squared plus 1 to the power of -1, do a chain rule on it? Could you call the top f1 and the bottom g and do a quotient rule on it? You'll get the same result, and that goes in there. Now, here's something that's going to save you some time. Because we are doing this at -1, I can only do it here. I have to do this algebraically, but can I plug -1 into all these guys? Now, if I plug -1 into all these guys, can we just pretend that the answer's 4, 3, and 5? Making numbers up, right? But there will be numbers, won't they? There'll be 3/5, 4/5, and -1/5, right? There'll be numbers, right? Can I then find the magnitude of that vector the usual way? Which will, in this case, if this was right, that'd be 1625, that'd be square root of 50, right? And then can I just take this guy into that guy and I've now got my unit normal with numbers. Now, how do I get my unit tangent? Don't I plug -1 in here? So what do we get? 1/3, -2, 2, and 1. So the unit tangent will be -2/3, 2/3, 1/3. So that's their answer. You do this combination, you've got the second answer. And you know, can you imagine that's 4 over square root 50 and all the good stuff? So how do you get the unit binormal without doing anything tedious? Because this is the end of tedious. This is just number crunching now. Don't you take the numerical value of this fella, cross product with the numerical value of this fella? And that is the process that I would use to find the unit tangent, the unit normal, and the unit binormal. Is there, I know I talked through that, but is there enough clues to the process that you would do? Differentiate with t, differentiate with t, plug in t as -1, so this turns into a number. Use that number to get its magnitude. Once you know the magnitude in this vector, can't you make it a unit vector? And that's who t is. You already have this algebraically. If you plug in -1, you now have the answer that you're looking for as a unit tangent. You do a cross product of this fella with the numerical value of this fella, and you will get the numerical value of the last one, the binormal. So the reason I'm doing that is save time, right? Less work, the better. Are we good? Right, long questions. Fraught with possibilities of mistakes. So let's look at velocity, acceleration, and speed. I'm going to take a very simple space curve to do this to, just to get the ball rolling. T squared plus 1, 2t, 5t minus 1. So that's a pretty boring space curve, right? It doesn't have any interesting shapes I can think of. If you want to find the velocity vector, and think back to Calc 1, and we have mentioned this before. What is the velocity vector? What's its connection with this guy?
Isn't it the first derivative?
Yeah. So in a lot of ways, these questions are less tedious in the process, because don't you just need to find the first derivative? You don't need to do anything else to it, just find the first derivative. In this case, 2t, 2, and 5. Make my life very easy right now, right? Now, how do you get acceleration? Well, isn't the acceleration the double derivative of the space curve? You know, like back in Calc 1, was it the first derivative of s of t, the velocity, and was it the second derivative, the acceleration? You remember that? Some do? Okay. Now, in this case, you get 2, 0, 0. The acceleration vector is a vector. It is not a scalar. And that is because when you move in 3 dimensions, you have 3 components of acceleration. In other words, you'll be accelerating in the x direction at a different amount than if you were in the y or the z direction. So you can imagine that, you know, as a curve or some object moves, the acceleration, the change in velocity, if you like, in that one direction, may be changing at a different rate than the other two. In fact, can you imagine a space curve that flew parallel to the floor? Wouldn't its vertical velocity, I shouldn't really call it that, isn't its z-axis velocity 0? It's not moving up, right? Isn't its z-axis acceleration also 0? But horizontally, couldn't you have an x and a y and velocity and acceleration? Those, you know, you go fast, you go slow. Now, speed. Speed is the magnitude of the velocity vector. So in this case, it's 4t squared plus, yeah, I guess I did it in my head. Don't do things in your head. 2t squared, which gets you 4t squared, that's better, plus 2 squared, plus 5 squared. And so, now what I can tell you about this moving object is that isn't its acceleration only going in the x-axis? So it's changing its velocity in the x direction is the only one that's changing. Aren't these two fixed? And you can see it here. Isn't the velocity getting faster and faster and faster only in the x direction? The other two are stationary. Do you know this object would be traveling essentially parallel to the x-axis, getting faster and faster as far as velocity is concerned. The other two are not going to, I mean, there'll be a number, right, but it won't be specific. This is the speed. And what does the speed tell me? Well, if I look at this object, this function, just as a normal function of t, I can calculate the minimum speed. Why is the smallest number that speed can ever be this value? Looking at this function here, how can I make that conclusion?
Even when you're at 0, you still have a root 29 with it.
Right, and won't this always be a positive number, so everything else is going to be more than it? That's why I know this is a minimum. Would you agree that this function, theoretically at least, as t gets bigger, doesn't the speed get bigger? You know, at t equals 10, it's big, but at t equals 1,000,000, it's scarily big, right? So what that tells me is I'm getting some insight into the movement of this object, right, this space curve. Doesn't it always do at least the square root of 29? And that's only going to happen, what, at t equals 0? And then as time travels, doesn't it just get faster and faster? But isn't it doing it in such a way that only the x direction in the movement actually gets faster? Don't the y and z stay pretty much the same number, 2 meters a second and 5 meters a second? So that object to me is traveling roughly in the x-axis direction, getting really fast. So that's a spaceship shooting off somewhere in one particular direction. We cool with that? In a lot of ways, do you see how these guys are much easier to handle? The next one I'm going to do is a helix, and then the one after that is just, we'll pick some ridiculously ugly thing just to show you the math of it. So here's my second fella. I'm going to do one of my friends a helix. Okay, this guy's a helix. Would you agree this is a helix traveling vertically upwards on the z-axis? Agreed? Z-axis, helix, spiraling up. Let's find the velocity vector then. You differentiate this, remember the 2, you get 6 cosines of 2t. You differentiate these, you get -6, the sine of 2t. And you do this guy, you get 2t. You want the acceleration vector, you just differentiate your velocity vector, and this time you'll get -12 sine 2t. This guy will get you -12 cosine 2t, and this guy here will get you 2. You want speed, then you get the magnitude of your velocity vector. So it's going to be the square root of this guy squared, and that guy squared. So we've got this fella squared, we've got this fella squared, and we get 2 squared. Okay, I'm going to skip some lines here. Won't that get you 36 cos squared 2? Change my mind, I'll write it down. 36 cos squared 2t plus 36 sine squared 2t plus 4. What does 36 cos squared 2t plus 36 sine squared 2t get you?
36.
Yeah. Do you know it doesn't matter if it's cos squared t, cos squared 22t, as long as it's the same number, don't cos squares plus sine squares get you 1? And multiples of them get you, in this case, 36. So that's going to be the square root of 40. what does this tell me about this particular helix, right? So it's going up the z-axis.
Wouldn't it be 36 plus 4t squared?
Did I screw up? Oh, okay. You're right. Okay. What does it tell me about this one? It spirals upwards. Doesn't it spiral upwards and get faster then as time goes on? What's the minimum speed of this guy? Would you say square root 36 is 6? Does it have a maximum? Nope. Anything interesting about the velocity? No, all the components are changing with respect to time. Acceleration, yeah, all the... Oh, wait a minute. Wait a minute. Did I go and change something that I shouldn't have? Nope. We're cool. I'm good. We're right. Okay, last one in the set then, and that will be the end of calculating velocity, accelerations, and speed, and then I'll do a little puzzle question at the end. Right. Going to go crazy in this one, but don't go too crazy because we all have to do it. Somebody tell me what the x one is. Give me a just random functions you want me to plug in there.
Te to the negative t.
Okay, cool one. Give me a y component.
Like square root of t or something.
Yeah, okay, I'm just picking that. Won't do 10 into. Right, I'm going to pick a fraction. Can we do a t plus 1 over t squared? Plus 1, right? So all I'm doing here is picking an ugly function just so that, you know, we can deal with it. The chances are that when you do the unit tangent and unit normal, you'll probably be fed up differentiating ugly functions, but let's do some practice with this fella. Right, if you want to do the velocity function, you differentiate this guy, you differentiate this guy, and you differentiate this guy. So I guess I should do this at working. If I want to differentiate this fella, isn't this going to be a product rule? So f dash j plus f of g dashed, that gets me 1 times e to the negative t plus t times e to the negative t times technically negative 1. So I will get e to the negative t minus t e to the negative t. Right, now if you want to do square root of t, don't you just call it t to the half? And then you can do essentially the power rule. So its derivative is multiply by the power, reduce it by 1, and then make it look pretty. And then for something like t plus 1 over t squared plus 1, wouldn't that be a quotient rule? So I'll call this f, and I'll call this g, and we'll have f dash g, take away f of g dashed, all over g squared. So what do we get? We get a 1, leave that guy alone. Take away t plus 1 times a 2t, all over t squared plus 1 squared. And what does that get me? It gets me a t squared plus a 1. Take away a 2t squared, take away a 2t. Looks like I'm going to have 1 minus t squared minus 2t all over that guy. And I may change my mind in a minute, but not yet. Okay. Would you agree that that is really just a process of differentiating from Calc 1 and just doing it 3 times? And I am going to change my mind. 3rd time. When I just differentiate that guy, That guy there would be what? Negative e to the negative t and a product rule. Couldn't I differentiate that guy and just convert that into 1/2 t to the negative a half and do a power rule? And you see that guy at the end, would you agree that is one horrendous quotient rule that I definitely don't want to do, but that's how you would do it, and you get your third guy. So, ... Now, if I wanted to get the speed, which is the magnitude of the velocity vector, it would be the square root of e to the negative t minus t e to the negative t squared plus that guy squared plus this fella all squared. And there's nothing pretty going to come out of that. So I'm just going to leave this guy alone. This guy does become a little bit nicer, and this guy doesn't really have much that we can deal with. The bottom can become a little bit nicer. So can you see that the speed is just an ugly square root? I wouldn't have expected it to be nice. You can imagine if you randomly pick functions, there's no way in the world that's likely to be nice. And we are good. So if I gave you any r of t space curve, do you feel comfortable about the process of getting velocity, acceleration, and then eventually speed? You feel comfortable, you know about how you're going to do it. The mechanics of it depend on what you're given. That'd be fair? Thumbs up it is. Now, a little side issue and then we'll leave this fella. Can you imagine I got a question and the speed ended up being that guy? Suppose I asked you to tell me where on the space curve does any particular shape have a maximal or a minimum velocity. So you want to know when it's going fastest or slowest. So I should say speed. Then doesn't it become finding out when this thing is at its maximum or its minimum? What do you think this is going to be? Do you think this thing has a minimum value that it never gets smaller than? Do you think this thing has a maximum value that it never gets bigger than? Just based on its shape. Any suggestions?
Its minimum would be 1, right?
Well, it's definitely got a minimum. I'm not saying you're wrong about the minimum being 1, but it's not oh, you're thinking this number? Not necessarily so, but it is a minimum. If you take the square root out, isn't that guy a normal happy-faced concave up parabola? What happens if you take, we'll assume that these numbers are positives because speed has no meaning in the complex world, right? So it has to be positive values. If you take the square root of this, don't you basically, it's like an elephant sitting on it. You basically just flatten it, but won't the minimum still happen at the same place? So my argument is that this function is a minimum, and all I need to do is find out when it is equal to its derivative is 0. And I don't need to do this. I don't need to have a function called this fella. Find its derivative, set it to 0 and solve. I only need to do this. Don't you only need to solve when is the thing inside the square root biggest or smallest to still know the place where the largest and smallest will occur? So that actually saves you some algebra, because if you want to differentiate this guy, don't you get 2t take away 8? Does it not make 0 when t is 4? And won't the speed be the square root of 4 squared take away, oh, shooting space, take away 8 fours plus 1, and you'd get your answer. But I can fix that. Doop, 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 doop. Can I? Forget it. The process is right. The question, I've gone and screwed it up by just picking something that gave me a negative square root, which is kind of weird. Can I do a better one? Let's try one more. Suppose speed is this guy. Then don't I need to just find out the minimum value of this fella? And if you differentiate to, oops, t squared in there, you put a derivative of this guy, you set it to 0, t equals 0, and the speed ends up being, just being 1. Okay, that was a very simplistic one. What's the time like? I'm going to go and look at some homework questions because they give me examples that don't turn out funny. Right, so we've done curvature, so I'll skip that. And
Do you have a question about that last problem that was on that one you had up?
right, yes.
It says like cosine h and then t.
Oh, does it say hyperbolic cosine? That's what cosine h then t is.
Yeah, it does.
Oh. You know, the hyperbolic cosine is just like a cosine. It's a slightly different rules to it. But if you differentiate the hyperbolic sine, you get the hyperbolic cosine. If you differentiate sine h, it's called sinh. At least that's how I pronounce it. It's just a function. What was it? You've just never seen it before, I'm assuming, right?
No, I'd never seen it, so I was kind of.
Yeah, we tend to avoid that guy. I think it might have just sneaked in because I never noticed the h either. That was in the previous section, wasn't it? That was the one I just closed. Is that what you're saying?
Yes.
Is that right? So I'm not going to close it yet. I want to go back in and look at that damn thing so we can show everybody what's going on and what we're going to do about it. This is arc length and curvature. Yes, it was under arc length and curvature. You can't remember which number it was. Just make it easier for me to scan to.
The very last one.
Oh, okay. That's easy to find. Oh, I see it. Right. Oh, interesting. I think when I chose that question, I didn't notice the h. I just thought it was a sine and a cosine. In other words, I just thought it was a helix. No, I don't think it's fair. I'll just kill that question. Can you imagine it was 4 sine t, 4 cosine t, and z was 4t? If it was, that question would be totally fine, right? It would be doable. If you want to, let me kick back and I'll show you rather than say it. If you wanted to differentiate the hyperbolic sine cosine function, it's not that difficult to do, even if you've never seen them before. But I don't want to introduce something you've never seen. It's a bit unfair. I'm having issues with my screen right now because I can't find the button I want to press. Here we go. Right. If you have the hyperbolic sine function, it looks just like sine t, doesn't it? But with an extra h. If you have that function and you want to differentiate it, because that's all you want to do, its derivative is a hyperbolic cosine function. If you differentiate the hyperbolic cosine function, it's the hyperbolic sine function. Do you notice that the difference here is that it's positive in both cases? Why does it even get a name that sounds like a sine and a cosine? That's fascinating. If you wanted to know what the hyperbolic cosine of t is equal to, it's that guy. I know it's got weird eyes in it, but they all cancel out. It's a weird function. It gets employed in very few examples. One of the reasons it's called the hyperbolic sine and the hyperbolic cosine is that its power series is identical to the power series of a sine function, for instance. And the only difference is that all the terms are positive instead of positive and negative, which is kind of esoteric. This is the only example I can think of where the hyperbolic cosine or sine function gets used. Can you imagine you had a tower that was 100 and another tower that was 150, and you had a piece of string that was a certain length? Let's say the piece of string, and let's have the distance between here and here, that's important. Let's have this as 400 meters. And let's assume that the piece of string I had was 500 meters long. If you placed a piece of string that was tied at these two ends and you just let gravity do its thing, can you imagine that you would get a unique curve made by a rope that was 500 meters long? Do you see that curve? The formula for that curve is given in terms of the hyperbolic sine or hyperbolic cosine function. And I guess people who build bridges, it might be useful for them to have such a function because it models, curvature on ropes and things better. Travis, what's your question?
Is that based around Euler's identity?
Tell me Euler's identity. I don't know that one by that name, but that's not a surprise to me because I know lots of things by other names. What does Euler's say?
E to the power of I pi.
Oh yeah, that I call that de Moivre's theorem. Do you call it Euler's? Right. E to the I theta is cosine theta plus I sine theta. And your question is it connected to that? And the answer is it is exactly connected to that. They use building blocks of this to generate the hyperbolic sine and hyperbolic cosine.
I thought it looked familiar.
Right. Well, for some of you, I don't know. Where did you find this guy, de Moivre's theorem?
On the internet.
Oh, okay. And they called it what, Euler's?
They call it Euler's identity when it's e to
on its own like this?
When it's e to the I pi, it equals e negative 1.
Okay. Yeah. So de Moivre did a lot more work on it, so that's maybe why I call it de Moivre's theorem. I think the one you're talking about is just a special case. Right, you know the sine of pi is nothing, and you know that's -1. So e to the I pi is -1. Is that the special case you're talking about?
Yeah, that's what I recognize.
Yeah, so it sounds to me, I'm making this up, it sounds to me like Euler maybe came up with this, but de Moivre ran with it and actually did more stuff with it, so they both get a little bit of credit. In fact, if you look up to it, it's quite interesting. Look up de Moivre's theorem and you can actually use this identity to do, to create all those trig identities that you can't remember. You remember the sine of A plus B, sine A cosine B plus cosine A sine A, all those guys? De Morphy's theorem allows you to do that. It also allows you to do things called roots of unity, where you look at a very simple question like if x to the n was -1, where n is a whole number, how many solutions are there in the complex world? They're called roots of unity, and there's I'm diverging. Some really cool math in that, but not the math we need to worry about. So I was going to, before I got some cool questions, I was going to go in and look at some examples using the textbook so that we could actually get numbers that wouldn't drive me crazy and go weird. So I'm hoping, guess that's the best.
Guarantee with the textbook.
Say that again?
There's no guarantee with the textbook.
Oh God, even they screw up. Well, not screw up, but they don't always give you an easy time. Well, they're more likely to give me an easy time than if I just randomly picked some vectors, you know, on my own. Right, here's some of the examples of what we're doing. The visual part is really, it's kind of cool, but you know. T squared 2, wouldn't the velocity, the acceleration, and the speed, because that guy there is speed. Would you agree that that's a baby question? I mean, I could do that right now. Wouldn't that be 1, 2t, and 0? And then that would be 0, 2, and 0, and then whatever the velocity is. And notice when you click on these guys, you get this. And I know it's a while, so just in case you forgot, if you differentiate this function, you get a 1i, a 2tj, and a 0k. So you would go 1i, you'd go over here to vectors, and you'd pick I. Oh, wait a minute, are you seeing this?
I don't think so.
Okay, I'm going to go out and in to show you what the heck's going on here. There, you seeing it now?
Yeah.
Okay, so I just hit the vector tab over here, and I'm going to write down the answer. It looks to me, because they're using ijk, that that's the format they want the answer to be. So if you differentiate t, you get 1i. If you differentiate the middle term, you get 2t. So that would be plus 2t. My keyboard is covered in paper. 2t. And won't I stick a j next to it? And the third term, won't the third term be 0? So nobody writes 0, okay, so we're good. Now, if you move on to the acceleration, won't the I component get you 0? And the second component, when you differentiate it, just gets you 2. So you're now going to get 2 j. And the magnitude of the velocity vector, which is the speed, that will get you the square root of 1 squared, which is 1, plus 2t squared, which is what, 4t squared? 4 t, and then I should be able to go up to here. And I hit that one, and that way I can put my square in. We cool? Now, there are 4 pictures here with velocity and acceleration on them. And so I guess we kind of need to pick the right one, but really when you're doing these things, and because you get 3 guesses, you're probably going to get it right anyway by guessing, and it's not a question I particularly like. You can also go on to, you know, the 3D software and just actually plot the damn thing, or actually plot both of them and then look at the picture and you'll be able to tell. All you'll see when you do it is the red and the blue, but that's enough to tell you what it is. I'm looking at the velocity. Isn't it going 1 in the x and 2t in the j? So what would that be? 1 in the x and 2t going that way. Yeah, could be that fella. It's definitely not that one. Could be this one. Isn't that one? So already I've restricted it down to 2. Here's a pretty standard one. velocity, acceleration. I wonder. Do you want me to do 3? I think it's going to come out nice. I know 4's a helix, so I know that will come out nice. There's an ugly one. Let's do 5. I think I'm going to do one. I should do an ugly one. So in question 5, it's going to be 8 square root of 2t, e to the 8t, and e to the negative 8t. And we are going to find velocity, acceleration, and speed, using those as our vectors. And excuse me, checking. Yeah, we have time. Okay, let's go for velocity vector. If you differentiate this guy, you just get 8 root 2. You differentiate this guy, you get 8 e to the 8t. If you differentiate this guy, you get that. The fact that you're not getting unit tangents and unit normals does make these questions a lot less onerous, aren't they? I mean, yeah, no biggie. If you want to get the acceleration, then a constant when you've differentiated is 0. This guy just gets another 8. And this guy gets another negative 8. Oh yeah, that is much cleaner. Now, I suspect that the speed is going to be messy. So let's see what we get. This guy squared. This guy squared. And this guy squared. Oh, 64 times 2 is 128. 64 e to the 16t. And this guy is 64 e to the negative 16t. And if I put this guy first, I put the number in the middle, and I put this guy at the end. Do you see a kind of sort of a, there might be some stuff we could do to make this pretty? Because we really should, when it's possible, simplify the speed one, this one here. Anything obvious you can do?
Maybe like reduce them.
Okay, how are you going to do it?
Pull a 64 out of the whole equation.
Sounds like a plan. Would you agree that there's a common factor of 64 here? If I pull that out as a square root, won't the square root of 64 get me 8? And I'll now be left with well, that was a good start, right? You agree it's already looking nicer. I got a square root with 3 things in it. What should I at least try to see if it's true?
If it's a square.
And it is actually, isn't it? What does this guy get you?
E to the 8t.
E to the
Great.
8.
8t. Don't you half the power? That's essentially the square root of it. What does this guy get you?
E to the negative 8t.
Can you trust me that if you follow that all out, you'll get a 2 and the other 2 terms? It's a perfect square.
Yeah.
Which means that we really have that. Now that is elegant. I mean, that is kind of cool. If I randomly try to make that happen, do you know, 9 times out of 10, I just get some really ugly square root thing that you can't do anything to. But that was elegant. That was kind of pretty. As I look at this function, do you know this function has no maximum or minimum speed? These, well, let's rephrase that. It has no maximum speed. These can be as big as possible. That function might have a minimum. Right? Is there a minimum velocity to this function? Well, let me try it out and see if there is. Right, this is the guy that we want to find out, is there any minimum? The reason I know there's no maximum, won't this number just get bigger and bigger forever? Right, so there's no top number. Right, if I want to take this fella and I want to find its minimum, couldn't I just find the minimum of this guy? Because I just want to know for what value of t does it happen, and then when I know it, I'll plug it in here. It's the same effect. Right, if you differentiate this guy, you get this fella, you differentiate this fella, you get that guy. You want to set it to 0, so you pull out that, which essentially tells you that that is, which means that that has to be true, which means that has to be true. A little cross multiply, and it makes that has to be true. If you take the natural log of both sides, that has to be true. Oh, after all that darn hard work, at t equals 0, you're going to get the smallest value. So the smallest speed for this function is going to happen when t is 0. So what does that get me? E to the nothing is 1. E to the negative nothing is still 1. 2 ones get me 2. I can now tell you that for this particular space curve, it will, the smallest, right, the lowest, whatever you want to call it, speed is going to be 16 meters per second. That was kind of interesting.